Hi everyone, welcome back to Math 111. This is Scott. Let's get started. What we're going to be talking about now is section 5.6, which has to do with rational functions. So it's 5.6, rational functions. So for us, this is the exciting finale of chapter 5. And what we are going to be doing now is taking a little twist on polynomials, making what are called rational functions. Now, the reason why they're called rational functions is that they are a ratio. So the first 5 letters say it all. They're a ratio of 2 polynomials. So the format is a polynomial over a polynomial. So anything that has a polynomial on the top and a polynomial on the bottom. And by polynomial here, what I just mean is anything that is made up of terms that have just powers of x that are not negative, not fraction, and maybe some constant terms. Okay, now the first thing that you notice is that there is a division. And whenever there's a division, the little hairs on the back of your neck should stand up, and you should be nervous about the domain, because dividing just invites you to accidentally divide by 0. So let's get that out of the way. So the domains of rational functions are always going to be everything that does not cause you to divide by 0. So the domain of a rational function is the set of all real numbers often called all reals, except x values that would cause the polynomial in the denominator to be 0. And by denominator, we mean the bottom of the fraction. So it's the divisor. So as an example, let's take something like this. Find the domain of, and let's say f of x equals x squared minus 9 over x squared, let's say minus 5x plus 6. So you do not even look at the top. Do not even let your eyes wander to the numerator. All of the action in the domain question is in the denominator. So you just look at this, and we just announce what we need. We need this to not equal 0. Well, this can be factored, so it can be factored into an x minus 3 and an x minus 2. Which then leads us to x minus 3 shouldn't equal 0. X minus 2 shouldn't equal 0. Which leads to the conclusion that x can't equal 3 and x can't equal 2. And we can now just announce that as our domain. So this is the way your book describes the domains in these particular problems. So you could do this in interval notation, no reason not to. However, it gets a little bit cumbersome from time to time, putting every domain in interval notation. And the important thing is this fact right here, not 3, not 2. So we could say all reals with x not equal to 2 or 3. So all reals except these. And that's the domain. Now notice that we found the domain before doing anything at all with the top. We did not simplify this in any way. And that's an important fact, so note. Find the domain prior to doing any simplification. Don't cancel any factors from the top and bottom until you found the domain. Before doing any cancellation of factors from the top and bottom. Okay. Once you have found the domain, though, then you can let your algebraic horses run free. Then go ahead and do all the simplification that you want to your heart's desire. So once you find the domain, go ahead and cancel. Cancel away. Cancel. Any factors common to the top and bottom. Now, if you manage to cancel away an entire factor from the denominator, then that produces what's called a removable discontinuity. So if any factor is canceled completely from the denominator, that produces what's called a removable discontinuity. Or hole, it's also called, in the function. So for example, if we go back to that f of x, which equals x squared minus 9 over x squared minus 5x plus 6. This, if we were to now factor the top and bottom, we'd have x plus 3, x minus 3 for the top. It's a difference of 2 squares. And then the bottom, we'd still have x minus 3, x minus 2. just like before, but now notice the x minus 3's cancel, and so there's a removable discontinuity at, and then what you would just do is look at the value for that. So x minus 3 equals 0, meaning x equals 3. So there's a removable discontinuity at x equals 3. And the reason why this is called a removable discontinuity is that once you have done the cancellation, then all of a sudden the value that you could have put in there, or that you couldn't have put in there before, now all of a sudden can be put in there. So then what you would do is you would take the function that is produced, and you can actually now plug in what used to be a forbidden value. And that's why it's called a removable discontinuity. So at that value, the simplified version of f can be evaluated. And so we would get a y that equals 3 plus 3 over 3 minus 2, which will give us 6 over 1, or in other words, just 6. So then what that means is there's a point. So the point, which had an x-coordinate of 3 and 6, is the removable discontinuity which means, in other words, there's a little hole in the graph. And we'll look at what that means in on Desmos in a second when we get around to looking at what the other features of a polynomial, or sorry, of a rational function, what they all look like. Okay. So that's what happens when we have factors that cancel out of the denominator. However, if there are factors that continue to exist in the denominator, those produce a vertical asymptote. So factors that survive in the denominator produce vertical asymptotes. And what those look like, so the look of those is this. So the appearance. If it has odd multiplicity, so if the power in the denominator is odd, then it will look like a reciprocal function. So this is if it's odd multiplicity. Or if it's even multiplicity, it will look like the reciprocal square function. So it'll either look like the reciprocal function or the reciprocal square function, depending on the multiplicity. And they can both be oriented the other direction, where the left side could be up and the right side down, or vice versa. So, vertical. Vertical asymptotes resemble the reciprocal function from the toolkit. If their multiplicity is odd, or the squared reciprocal function if even. So in other words, if their multiplicity is even. Okay, so far we have now tackled the denominator. So and that's the complete story of the denominator. So factors of the denominator. Now let's summarize that. Factors of the denominator. If they cancel, that makes a removable discontinuity, and if they don't, then that makes a vertical asymptote. If they cancel away, removable discontinuity. If not, vertical asymptote. All right, so that's the denominator for you. Now, as for the numerator, that's a different matter. So the numerator is the top of the fraction, and there's no law against having a 0 on the top of a fraction. It's only the bottom of the fraction where zeros cannot live. And if there's a 0 on the top of the fraction, that makes the whole fraction equal to 0. So the numerator factors. These, as long as they don't get canceled out, these produce the zeros of the function. In other words, the X-intercepts. So if they don't get canceled, the factors of the numerator produce zeros. Zeros of the function, in other words, X-intercepts. So there, once again, the effect of the multiplicity is the same as it would be with with the polynomials. So the effect of multiplicity is the same as with polynomials. So in other words, they go right on through if it's multiplicity 1. They bounce off like a parabola if it's even multiplicity. And they wiggle through like a cubic if it's odd but bigger than 1. And all of these can also be oriented upside down. Alright, now let's return to that little example and see what there is to see. So the little example that we were dealing with was f of x equals x squared minus 9 over x squared minus 5x plus 6. Well, once again, as we know, it can factor x plus 3, x minus 3 in the top, x minus 3, x minus 2 on the bottom, these factors cancel, producing a removable discontinuity, as we already mentioned. But then over here, what we have is x plus 3, x minus 2 on the bottom, and these two, the two remaining factors, each contribute their own little piece to the puzzle. So this means that if x equals 2, then this will be dividing by 0. So that's a vertical asymptote. And because it has only an exponent of 1, that means it's a multiplicity of 1. It's a vertical asymptote of multiplicity 1, which means it's going to look like the reciprocal function. And from the top, we know that x equals negative 3 will be a 0, also multiplicity 1. So what we've got here is a removable discontinuity, and as we already figured out, it was at, what was it? I was at 3, 6. Vertical asymptote at x equals 2, and then 0 at x equals negative 3. Now, just as with polynomials, when it comes to finding the intercepts, the zeros are the same thing as the x-intercepts, and then for the y-intercept, you would just plug in 0 for x. So the intercepts as usual come in two flavors, the x-intercepts and the y-intercepts. So x-intercepts, these are the points where the function is 0. In other words, the zeros of the function. And then the y-intercept is when you plug in 0 for x. This is the point corresponding to x equals 0. So you plug in x equals 0 to get the y-intercept. And you can do this, you can plug 0 in for x either in the original version of the function or in any simplified version, it doesn't matter. So you can plug in x equals 0 into, or I should say, for any version, simplified or not. Of the formula. Whereas these are the zeros of just the numerator. So the zeros of the numerator produce the x-intercepts, and then plug in x equals 0 to get the y-intercept. So returning to that old example, if f of x equals x squared minus 9, x squared minus 5x plus 6, of course, as we know, this simplifies. X plus 3, x minus 3, x minus 3, x minus 2, cancel, cancel, x plus 3, x minus 2. But now if we are looking at it specifically for the intercepts, we already know the x-intercept is when x equals -3. So then that gives you the point -3 for x and 0 for y. For the y-intercept, we can just plug in f of 0, if it's defined anyway. If it's not defined, we just say none. 0 plus 3 over 0 minus 2. You can use any version, simplified or not. So that's going to equal just 3 over -2, so just -3 halves. So it's going to be -3 halves, comma, 0. Alright, those are intercepts. Now there's one more piece of the graph of a rational function that is substantially different from polynomials, and that is what happens in its end behavior. So the end behavior. Of rational functions. Now this is a little bit complicated, and we can just break it down into a few cases, but the basic idea is that if we look at the leading terms of the top and the bottom, that will tell you what to expect in the long run for the rational function. So the basic idea the leading terms of the top and bottom polynomials determine the end behavior of the rational function. Now, there are several cases. So, first case. So the different cases that can happen is when you just look at the leading terms of the top and bottom, and if all the x's will cancel out of the top and will only survive in the bottom, and that means that the bottom will be higher degree than the top, and so then it will be dividing by larger and larger numbers and overwhelm the top. So the cases. Case 1. Degree of the bottom is higher than the degree of the top. The degree of the bottom is higher than the degree of the top. So for example, if f of x is something like 2x cubed plus 3x squared minus x plus 1 divided by x to the 4th plus 2x squared plus 1. Something like that. So the degree of the top and the degree of the bottom are 3 and 4. And then in the long term, f of x can just be considered as these two terms, 2x cubed on the top, x to the 4th on the bottom, and that cancels a little bit, and so that just leaves us with 2 over x. Then what that means is that the end behavior of this is going to resemble actually for the larger values of x, it'll resemble the horizontal asymptote you observe with the reciprocal function. So in all of these cases, there is a horizontal asymptote at y equals 0. And then depending on the power of the x that's in the denominator, it's either going to be approaching that asymptote from the top on both sides, or it'll be on the bottom on both sides, or it will be one up, one down. So the degree of the x in the denominator after canceling will determine whether it approaches the horizontal asymptote from above or below on each each side of the x-axis. So here, if you plug in positive numbers, it'll be positive. If you plug in negative numbers, it'll be negative. So even though they're both going to 0, it's going to be positive on one side, negative on the other. That's case 1. Case 2. Maybe the x's don't survive in the numerator or the denominator, and that happens if the degrees are the same. So the degree of bottom equals the degree of the top. So if they have the same degree, then all the x's will cancel away, and it'll look like this. For example, f of x equals x squared minus 9 over x squared minus 5x plus 6. So then, the long-term behavior of f of x is going to look just like the x squared over the x squared, which just cancels to make 1. And whenever the degrees are the same, it will always just cancel the x's away, and all that will be left is the coefficients. And what this means is that in the long term, the function is going to have a horizontal asymptote at that value. The y values of this function will be getting closer and closer to 1 the bigger and bigger x gets. So then there is a horizontal asymptote at the y value produced when the x's cancel. So in other words, the ratio of the leading coefficients. Okay, so that's case 2. Case 3. If the degree of the numerator is bigger, if the degree of the top is the bigger of the two, then we actually break that down into a couple of cases. Maybe it's only one higher. Maybe it is higher still. So let's say that the degree of the top is one more than the degree of the bottom. So if it's one more than the degree of the bottom, then what happens is this. So for example, f of x equals x squared plus x plus 1 divided by x minus 2. So we have is an x squared on the top and an x on the bottom. So the degree of the top is one higher than the degree of the bottom. What this means is that there is going to be a linear function that this will approach in the long run, but it's not going to be horizontal. It's going to be what is called a slant asymptote. There is a slant asymptote, also called an oblique asymptote, or oblique asymptote at the line produced by taking the quotient either through polynomial long division or synthetic division, either one. Either through polynomial long division or synthetic division. And for synthetic division, it has to be specifically in this form with the polynomial on the bottom having being just a linear with a leading coefficient of 1. So polynomial long division or synthetic division, where synthetic division is possible. So then here we would be doing the synthetic division like this. So 2, just playing the role of k, and then 1, 1, and 1 for the coefficients. So down comes the first coefficient to make the first piece of the quotient. Then you do 1 times 2, you put that over here, then you add those, and that's going to make a 3. And then really the next term doesn't actually matter, but we're halfway there, so we might as well do it. So you multiply 3 times 2, that makes a 6, and then that's a 7. This is the remainder, which actually doesn't matter that much to us, but the quotient does. And here this is the x term, this is the constant term. So the quotient is x plus 3. And so what that means is that there is going to be an oblique asymptote or a slant asymptote at y equals x plus 3. So this is the remainder, not relevant. Not relevant here. It's relevant for other things, but not for this. Now, that's case 3. Case 4. Case 4. This is when the degree of the top is bigger than the degree of the bottom, and not just by 1, but just in general. So, degree of top is greater than the degree of bottom, even plus 1. So what happens here is that we end up with a long-run behavior that is not an asymptote, but is called an asymptotic polynomial. There's an asymptotic polynomial at the quotient produced by dividing, either long division or synthetic division. For example, For example, let's take something like x cubed minus 1 divided by x, so this is f of x, minus 1. So what we've got here is a, actually let's make it x plus 1. What we've got here is a polynomial where the top has a degree 2 more than the bottom, and so we can actually just do the long division again, either through synthetic or polynomial long division means, and we can do k here of -1 if we're going to do synthetic division. It's going to be -1, and then the coefficient on x cubed is 1, x squared is 0, x is 0, constant is -1. Then down here, the degrees are all going to be 1 less than that, so it's going to be x squared, then an x, then a constant, and then a remainder. Remainder we don't care about, but these we do. Okay, so first comes that number, then you do this times this, and that produces -1, and then that goes there. Then you add, it's -1, then you do that times that, and it makes a +1, and then you add. And you do it again, not that it matters, and then it's a -2. But we don't care so much about that. And so there is, so the quotient here, the quotient is x squared minus x plus 1. So there's an asymptotic polynomial at x squared minus x plus 1. Just say y equals. Okay, so at y equals x squared plus, or minus x plus 1. Alright. Now, all of these pieces can be put together to make a graph. And that's actually the exciting part of all this. So putting all the pieces together to make a graph. So here's what we need. So here are the ingredients. The ingredients we'll need. So here's the recipe for making a delicious graph. So the recipes that we're going there. So the recipe calls for the following ingredients: the intercepts. So find the intercepts. So for the y-intercept, just plug in 0. For the x-intercepts, so for the x-intercepts, we find zeros of the numerator. Find the intercepts. Also, find any removable discontinuities. Find removable discontinuities. Then, let's find vertical asymptotes. Then find end behavior. And then once we've got all of these pieces, we can put them together to make a graph. So then sketch the graph. By So here's how we're going to start it. Start by just putting down points for all the intercepts and the removable discontinuity, and put little dotted lines for the asymptotes. So put points, for the intercepts, and dotted lines for the asymptotes. Both vertical, horizontal, and even slant, if that should be the outcome. Also, put an open circle for any removable discontinuity. Okay, then comes the fun part. So when it comes to sketching it, work your way from the end behavior inward, is my advice. So draw the graph from the end behavior inwards. So from the end behavior inwards, and then at each vertical asymptote, veer upwards or downwards making sure not to cross the x-axis except at x-intercepts. Then, once you've veered properly upward or downward, then you reappear. Then reappear, let's say either above or below the x-axis according to the multiplicity. Okay, so at each vertical asymptote you veer upwards or downwards, and it all depends on where you are allowed to cross the x-axis. And then you reappear either above or below, all depending on the multiplicity, and then use the multiplicities of the x-intercepts to orient the positive and negative parts of the graph. Okay, well, enough talk. Let's try this. So let's try doing this for each of the example, or for several of the examples that we've already looked at, and then maybe a couple more. So let's start with, as an example, our old friend f of x equals x squared minus 9 over x squared minus 5x plus 6. Well, as we already know, we know all the stuff about it, and now the question is just going to be making the graph. So we'll factor the top, factor the bottom. Alright, so those cancel, and so then once that has cleared away, we have an x plus 3, we have an x minus 2 left over. Alright, so now there is a removable discontinuity happening at x equals 3, and then 3 plus 3 will give us the y value. 3 plus 3 over 3 minus 2 is 6, and so that gives us the point of 3, 6. So 3, 6 is the removable discontinuity that we observe here. Let's see, vertical asymptotes. So look at the denominator, and we see that x minus 2 can't equal 0, so x equals 2 will be a vertical asymptote, and its multiplicity is 1. Good to know. X-Intercept. Well, we already found that it was at x equals negative 3, also multiplicity 1. So that means that the intercept is going to be negative 3 for x, 0 for y. And at the y-intercept, we're going to just plug in f of 0, and that equals negative 3 halves, and so that's going to give us 0 comma negative 3 halves. And then for the end behavior, we take a peek at what only the leading terms of any version of f of x would be, whether the initial one or the eventual one. And so that's going to be just an x over an x, or you could think of it as just being an x squared over an x squared. In either case, they cancel, and that makes just a 1. So that makes a horizontal asymptote at y equals 1. Okay, these are all the pieces. We already knew all these, but just want to see how the process generally looks. So now we just put the pieces into play. So horizontal asymptote, let's draw that in as a dotted line when y equals 1. What else do we need? We need an x-intercept at negative 3, 0. So that's going to be, let's say, right there. We need a y-intercept at 0, negative 3 halves. So it's going to be a little bit further down than that one. We know that there is a vertical asymptote at x equals 2, so it's going to be like this. And then at x equals 3, there is a removable discontinuity, which we'll draw that when we get there. And then let's just work our way from the outside in. So we just come down from the horizontal asymptote that we were writing along in the long run. We've got a date with an x-intercept right here, and a y-intercept right down here. And then we just keep on going, and then on this side, because it's an odd multiplicity, we come down, and then there's a missing point at, let's say, that's 3, 6. My scale is a little bit inconsistent, but that's what Desmos is for, to make good graphs. We can make, we can make what we can make, but Desmos is how we make more accurate graphs. Our goal here is just to make make a vague picture, x equals 2, of what these are supposed to generally look like. So there's that. Let's try now. Let's try now an example like this. So let's go f of x is equal to x plus 1 over x squared. Let's go minus 6x plus 9. Alright, so the important things to notice about this, we look at the top, we look at the bottom, we would factor. So it's going to be x minus 3, x minus 3. So in other words, x plus 1 over x minus 3 squared. Well, looking at the top and looking at the bottom, and again, we find the pieces of this in no particular order. So x plus 1 equals 0 would mean that x equals negative 1. So that is going to produce an x-intercept at negative 1, 0. And the multiplicity here is 1. As for the y-intercept, f of 0, you can plug this 0 into any form of the formula, whatever is easiest to plug a 0 in for. And the easiest place to plug in a 0 would be just in the original version, because that's just going to be a 1, that's just going to be a 9. Okay, so there's the y-intercept, and now let's see. Vertical asymptote is happening at x minus 3 squared equals 0, so x equals 3, but that has multiplicity 2, which means it's going to resemble a reciprocal square type situation. Now, let's see, end behavior. The end behavior is going to be, in the long run, we're going to have f of x approximately x and x squared, and since that's a denominator bigger than the numerator, that's just going to be like 1 over x, which in the long run is negative and tiny and then positive and tiny, which means there is a horizontal asymptote at y equals 0. And it's below on one side, above on the other. That's going to help us in making the graph. Alright, and those are the pieces. The pieces we need. So now we just, and there are no removable discontinuities because no factors canceled. So what do we have? We have a vertical asymptote at x equals 3. We have an x-intercept at negative 1. We have a y-intercept that is small, 1/9. So this will be my scale. Now, other stuff that we know that there is a horizontal asymptote at y equals 0, and we know it's just below the function is just below that horizontal asymptote on the left and just above it on the right. And then we just kind of work our magic. So we are going along the horizontal asymptote here. Got to go up through there, yep, up through there. And again, we'll let Desmos tell us what these graphs really look like. We're just doing the best we can here. So it spikes up because we can't go down. There's no X-intercept over here. And then comes from above. So the important thing is it's below and it's above. So here's an example of one where it is a slant asymptote. So this is example C, and let's say f of x is equal to, let's go 3x squared plus x minus 2 all divided by x minus 1. Now we'll start by factoring this as usual. The factoring on the top is a little bit harder than we've usually seen, but we can do it. It's going to be a 3x and an x. That's a good anchor. And then we need two things that multiply together to make negative 2. So that's going to be 2 and a 1, one of them negative. And one of them is going to have to be over here, one of them is going to have to be over here. And when we multiply it all out FOIL style, going to have to end up adding up to an x. So that means we're going to need the negative 2 to be added to the positive 3. So it's going to have to be like that. X minus 1. And so then what we are going to end up with is from the top, we've got 3x minus 2 equals 0 means 3x equals 2, which means x equals 2/3, and that has multiplicity 1 because of the fact that it doesn't have an exponent. So that means there's an x-intercept coming at that x value. X plus 1 equals 0 means x equals negative 1, also multiplicity 1. So then there are x-intercepts at x values of 2/3, 0, and an x value of negative 1, y value 0. Now for the y-intercept, just plug in 0 for x, f of 0. So you can plug 0 in for f, in for x, into any of the versions of the formula, including just the first one. So that could be just a negative 2 over a negative 1. So it's going to be 2. So that means we're going to have 0, 2 for the y-intercept. Now, vertical asymptotes, those come from the denominator, and so that's where the x minus 1 is going to come into play. So x equals 1, multiplicity 1. And then for the end behavior, because we have degree 2 on the top, degree 1 on the bottom, we are going to take the original version of the polynomial and we're going to do synthetic division. So we're going to have k equals 1, so it's going to be a 1, it's going to be a 3, a 1, and a negative 2 for the coefficients. X squared, x constant. And then down here, we're going to make an x, a constant, and a remainder, which we don't care about. So down comes the leading coefficient on the top. So then multiply those, and that'll make a 3. Then you add, that'll make a 4. Then you multiply, and that'll make a 4. There's 1. And then that gives us a 2, not that anybody cares. And so that gives us 3x plus 4, and that's the slant asymptote. Okay, now the way this is all going to look is as follows. So we draw in the slant asymptote. So that makes a 4 right there. Let's see, a y-intercept is going to be right there. We have x-intercepts at -1 and 2/3. Now it's important here that we know if the -1 is going to be above or below this line. It'll affect our graph a lot. So -1, if I were to plug that in, that'll be -3 plus 1. So it's going to be before that, so it's going to be like right there. And then what else? We've got another x-intercept at 2/3. It's going to be in a little bit more. And then let's see. Last thing about it, we need a vertical asymptote at x equals 1. So it's going to be a little bit past this one. And notice it makes a little crisscross pattern here. And then the way the graph is going to end up looking is it's going to be going from the slant asymptote into there, through there, through there. It's going to be going down like that. And then up here, what we're going to end up with is something that looks like that. Okay, now let's see how we did by checking all of these graphs with Desmos. So on Desmos, we will graph these same rational functions and see how we performed. Okay, now let's have a look on Desmos at the graphs of the functions that we just drew and see how we did. So you just go to Desmos and you start graphing. Alright, first off, f of x equals, we'll take the first function, x squared minus 9 is the top, and then divided by x squared minus 5x plus 6 is the denominator. Alright, so that is what the graph looks like, and we can put in some of the extras like the horizontal asymptote that we know of y equals 1, and the vertical asymptote we know of x equals 2. And there we see Desmos rendition of our graph. Take the grid off so we can see it better. Okay, so that's what Desmos says it looks like. We can zoom out, zoom in, and get a look at it. Now compare that with how our graph looked, and you'll see that it's a little smoother than ours is, perhaps, but the basic graph looks the same. One thing that is interesting about it, though, is we have the missing little point at 3, 6 that you can't actually see from Desmos, from the Desmos rendition. Now, if you were to scroll right along the graph until you got to 3, you'll notice that technically, actually, there is a tiny little hole there, but you can't actually just see it visibly. You have to know where to look in order to find the holes on Desmos. Most things that graph functions, whether they're calculators or online like Desmos, won't automatically show you the position of the removable discontinuities. So there's a tiny little hole that we know exists, but we can't actually see it right there. And then if you try to plug in f of 3, you would see that it is undefined. So it is not in the domain, even though you can't tell that just from looking at it. Okay, so that was the first graph. What was the second one? The second one was x plus 1 on the top. And then the bottom had x squared minus 6x plus 9. Okay, we have other important things such as a horizontal asymptote at y equals 0, and we have a vertical asymptote at x equals 3, and it's of multiplicity 2, which is what gives it that characteristic reciprocal square shape. So that's what so that's what Desmos says, and then ours, in contrast, looks like that. So again, Desmos is a little bit smoother, but some things are harder to read off of it. For example, it's hard to tell from the Desmos version about the X-Intercept that we know exists at x equals -1. Now, if you click anywhere near it, Desmos will realize that you are interested in that point, and it will show it to you. But we had to, again, go looking for it. Alright, and then the third one, the third graph is going to be the function f of x, which equals 3x squared plus x minus 2 on the top. And then on the bottom we have just an x minus 1. Okay, now here we don't have a horizontal asymptote anymore. Now we have a slant asymptote. So we have y equals 3x plus 4. And then we have the x-intercept at x equals 1. Sorry, the vertical asymptote at x equals 1. The x-intercept is of course at -1, 0, and 3/2. Looking at the wrong thing. Okay, so now we can see on this one the slant asymptote. Just gotta zoom out a little bit till we get a good view. The slant asymptote and the vertical asymptote together make a shape that is called a hyperbola in between them. And you'll notice that right along this line is where it is going, and then it's got a swoop and a swoop. Now we needed to know some of the locations of these points in order to orient our graph properly within those two, but it's something that takes a bit of practice, frankly. Anyway, so there's what Desmos drew, and here in comparison is what we drew. So ours looks like that. So again, Desmos is smoother and is a little bit more accurate as far as the scaling and things like that, but the basic picture is the same. All right. So now back to the notes. So now the last task of the section, and indeed the chapter, and in fact this whole piece of the course, is the following. Finding a formula from the graph. So we basically just take what we've been doing and turn it around in reverse. So the numerator factors. Make these out of the X-intercepts. Use the X-intercepts. And multiplicities. The denominator factors. For these, use the vertical asymptotes. And their multiplicities. But just like with polynomials, there might be one extra little factor in front, a little factor of a, and we can just use any other point or even the long run behavior to find the a. So use another point to get the initial factor, let's just say a. As an example, let's say we had something like this. So let's say we had x equals 3. Y equals 2. Oops. Say that this is at x equals 5. And then let's say we had a y-intercept of, let's say it was 10 over 3. Okay, so part of this we can just immediately spit out. So x equals 3 is the vertical asymptote, multiplicity 1. That implies x minus 3 in the bottom. X equals 5, multiplicity 1. That implies x minus 5 in the top. And so we already have most of the formula. F of x is equal to x minus 5 over x minus 3. But there's a mystery coefficient of a that we have to deal with. And the way we deal with that is we use the additional point that is given to us, 0 for x, 10/3 for y. So that means 10 over 3 is equal to the mystery a times -5 over -3. Multiply both, so the negative and negative cancel. Multiply both sides by 3, divide both sides by 5. And you'll get a is equal to 2. So then f of x is equal to 2 times x minus 5 over x minus 3. As another example, let's take the following. So we'll say at x equals 2, we have the following. So let's say it's so it goes goes like this, and let's say that this point right here is 1, 0, and let's say that furthermore we are told a point right here, which is very, very hard to see, but we can be told it. Let's say it's equal to 0, and then negative 1 over 5. Okay, well, let's take the pieces as we are given them. So x equals 2. This is a vertical asymptote that has apparently a multiplicity of 2, so that implies that we're going to have x minus 2 squared. And we know it's multiplicity 2 because to the eye it looks like a reciprocal square function, not like a reciprocal. So x equals 1. That one is just going straight on through, so it's apparently a multiplicity of 1, although it's a little hard to tell because it's so scrunched in there. So that tells us that we're going to have an x minus 1. So that tells us so far that f of x is equal to some mystery coefficient of a times x minus 1 on top, because that one is an X-Intercept, divided by x minus 2 squared. But then to actually find the value of the a, we need one more point. So we use the point that was given to us of 0, negative 1/5, and then that will be the y is equal to, so negative 1/5 is equal to a times 0 minus 1, so it's just going to be a negative 1, and 0 minus 2 is going to be a negative 2, but it's squared, so it's not going to be negative anymore. So that means that we've got negative 1/5 is equal to a times negative 1/4. The negative will cancel from the denominator, but not the numerator. Multiply both sides by negative 4 to cancel the negative on the one hand and the 4 on the other. And we're going to get a equals 4 over 5. So then that gives us a formula f of x is equal to 4/5 x minus 1 over, I should write it out differently. I should write f of x is equal to 4/5 times x minus 1 over x minus 2 squared. Alright, and that's going to do it for that. So join me next time for another episode of Math 111. Until then, bye!